Good morning, folks. This is CEO speaking for you again. It's 9 o'clock in the morning, as you can see on this binary clock. I know it's not very easy to deal with binary. So reading a binary clock, you have to be comfortable with it already. Anyway, today we are going to wire a diagram. This is going to be the one. I also know it's a bit too early to dive into the world of decoders because it's a very wide range of them. I'm actually using this diagram with decoders as a prop because the purpose is going to be to build a logic probe, a tool to help you measuring in circuitry. So to make your life a bit easier and to get a cheaper measuring tool than a complex multimeter. So for those of you who want to embed it into a case, it's going to look like that. So it's a Hammond case 1593D. And we're going to now discover the components making part of the diagram. So what the diagram is actually doing, I have one already wired here. So what happens is we have two kinds of decoders in the diagram. In the moment you want to start counting, so counting should be easy, okay? So it's counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and back 8, 7, 6, 5, and so on. So that one looks easy, okay? Now what happens is we're going to use a counter, which is a binary one with 4 outputs, and because it's counting 0 to 15, we're going to call it a hexadecimal counter, simply because it's able to count up to 16 combinations from 0 to 15, okay? Now what happens is if you want to display numbers 0 to 15 on one only figure, like here, something strange is going to happen. So let's see. Instead of showing you the number 10, because it's not possible to have the number 10 displayed on one figure, on one digit, you are going to see that very strange symbol here. So how do you know which is which? Unless you have a special display, like this one with 16 segments, or over there where I'm displaying the letter W and the letter S, and I found a way to distinguish between the letter S and the number 5, okay? So unless you have such special displays, or even better, if you can see it here, it's a dot matrix display. If you only have 7 segment displays, either this very small one or even a bigger one, is the same story, it's put upside down, then it's going to be difficult to figure out what these symbols are. So when dealing with counting for numbers bigger than 9, actually from 10 to 15, 10, 11, 12, 13, 14, 15, the manufacturer of this kind of special circuit called decoder is going to show us exactly here in the extract of the specs what you are going to see instead of these special numbers. So for 10, 11, 12, 13, 14, you're going to see some symbols, and the display is going to remain blank for 15. So let's take a look. So if we start counting, now was 9, so this is gonna be 10, 11 is like 10 if you take a look in a mirror, then 12, 13, 14, and for 15 the display remains blank, but you know the display is energized because you see the little dot which is energized, okay? So these are the symbols you're going to see, okay? If you are having a dot matrix display, of course you are able to distinguish the letters one by one, okay? If I just want to show you the letters, it's gonna be something like this. So it was A, now it's B, and then it's gonna be C, and then if we want to display the D, it's gonna be something like this. And then if you want to display the E is going to be this one, okay? And finally, if you want to display the F, it's gonna be like that, okay? So if you have a dot matrix display, it's easy because you can display the letters A, B, C, D, E, F, okay? So again, is A, is B, is C, is D, is E, and F, okay? So that's easy. But when time is coming to deal with our 7-segment display, we start to count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, and 15 is a blank display, okay? So this is what we expect to see. Now, the part of the circuit making it happening, here is the counter. This is the binary counter. We're going to use a 193. Here is the decoder converting the counting on 4 wires of the 193 into 7-segment display. So here is the counter, decoder, and the digit. So the decoder is called binary to 7-segment. And then we're going to have another kind of decoder, which is called 7442. And we're going to attach a bar graph to it. And what happens is something pretty similar to what you've seen, let's say, over an old elevator. When you go to the next floor. So now the 0 is lighting up, the 1, the 2, the 3, the 4, 5, 6, 7, 8, 9. So if you continue counting, as you can see, the numbers won't be recognized simply because the kind of decoder 7442 is not capable to recognize numbers bigger than 9. This is why it's called a BCD to decimal decoder, because BCD means it's only recognizing 0 to 9, and to decimal is because you have 10 potential outputs here, the green ones, and only one is lit at a time. See, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if I just do a little trick, I reverse 2 wires here, I'm gonna make it working in a different way. So now all the outputs are lit, excepting for the one we select, okay? If we go reverse, 8, 7, 6, 5, 4, 3, 2, 1, 0. And if you count it back, you reach 9. So only the 9 is off. And when you continue, all the lights they remain on because numbers bigger than 9 are not recognized. This is 15. So when going back to 0, you're going to see it again, okay? So, of course, we can reverse it back to make it working like before. So maybe that's gonna be easier for you because only one light is on at a time, okay? So now we're going to move where we're going to build a circuit. The packages we need to use. These are 7400 or the equivalent in CMOS, because is that part of the circuit on the left. We're going to build a debouncer for our micro switch. Actually, we have 2 micro switches because we want to count up or down. So we're going to build 2 debouncers, and then we attach the debouncers to the counter, and then we're going to see the counter counting in binary, and then we're going to attach the binary to 7-segment display decoder, and then we're going to wire the BCD to decimal decoder, okay? When we're going to do it, it's going to look something like that, because this one is working pretty similar to to the one you've seen before here. So this is going to show exactly the same way from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you continue counting, of course, all the LEDs of the bar graph are going to remain off because the numbers are bigger than 9. This was 15, and now it restarts from 0, 1, 2, and so on. Okay? Actually, I'm using that diagram as a prop for the moment we're going to build our logic probe. So the actually goal for all that is to prepare you for the logic probe, which is a very nice tool to use when taking measurements. And during the process, I'm going to take some measurements myself to show you how to do it. Okay? So on a trainer, we're going to replace these components one by one, and we're going to rewire it from scratch. Okay? Because in the moment you're able to follow just some simple instructions, even if you're not comfortable with these logic circuits so far, okay? If you just follow the instructions, having the components is going to be very easy to wire it actually, because we do both at the same time, the wiring and the troubleshooting, okay? So what we're going to do, we put our circuit off, because anytime you modify the wiring, the power should be off. And now we are just going to remove all the parts from here. Okay. As you can see, all the parts are going to be removed. Okay. And we're going to reconstruct everything from scratch. Okay. Take a look. We remove all the parts. Actually, don't even need to remove the parts. It's just enough to remove the wiring. Okay. So no more wiring. Okay. So we're going to start from scratch. Okay. So prepare a coffee, because we're going to start in 1 minute.